So in this tutorial, I'm going to be using Bayes' theorem on what is called the high-low deck problem. So this is let me outline the problem and then see how we can calculate. So the problem is there are two decks. One of which is called the high deck. It's a deck of cards. I'm going to just call it H. And the cards are as such. There's one ace, two twos, three threes, on and on and on, up until 9 nines and 10 tens. Okay, a total of 55 cards. Okay, the low deck has the exact opposite. It has more low cards than high cards. Notice the high deck has a lot more high cards than low cards. And so in the low deck, I have 10 aces, 9 twos, 8 threes, etc., 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 up to 2 nines and 1 10. And again, it's also 55 cards. And we're going to draw from this deck, and then and someone hands us a random. So the problem is, someone hands us a deck. We don't know whether it's the high or the low. We're going to draw cards from it and try to infer what the probability that we are holding the high or the low deck is. So imagine that that I have data of the form I drew a 7, and then I follow that by drawing a 9. Okay. And I'm going to do this without replacing the cards. So as I keep drawing, there are fewer and fewer cards. And there are what I call the easy probabilities to do and the hard probabilities to do. So the easy ones, which are the likelihoods, and we'll see where that comes into Bayes' theorem, are of the following form. Let's imagine I know what kind of deck I have. Let's say I know I have the high deck. What's the probability of me drawing a 7 and a 9? Well, I drew a 7. There's 7 sevens in the high deck, and there are 55 cards. Now, taking one card out, I have 54 cards, and there are 9 nines in that. So, out of 54, and so we can just calculate that as a decimal if we really want to, and I get about 0.02. Okay, so, fairly rare. Now I could do the same thing for, imagine, I know that I have the low deck, and what I get there is there are 4 sevens in the low deck, 4 out of 55. And then there are only 2 nines out of 54, and that gives an even lower chance than the first one, 0.00, about 0.0027. Okay, so those are those two probabilities. But these are what I call the easy probabilities. So essentially, we know the really important stuff, and we're calculating out the probability of observing certain things. Proper inference is usually not done in this direction. It's usually done in the other direction. We want to know the probability of this property of the world, namely whether we have a high deck or a low deck, given the observations that we have. We want to know the probability of the low deck, given the observations that we have. So these probabilities that we first, which I call the easy ones, all right, and they're also the less interesting ones, is related to the interesting ones, the interesting probability, via Bayes' theorem. So that's where we're going to go for that. And I'm going to use a particular way of calculating Bayes' theorem. It's doing it in 2 steps rather than one big long calculation. So let me outline that. Okay, so we're interested in the following quantities: probability of the high deck given that we observed a 7 and a 9, probability of the low deck given, so parentheses, the same observation. Okay, now Bayes' theorem says this is going to be proportional to, and there's going to be a scaling factor here. This is going to be proportional to, it's not equal to, the likelihoods, which are the reverse, assuming I know that the high deck, what's the probability of the data, and what's the probability of my data saying I know the low deck, times the prior probability for that particular model. All right. Since we don't know either one of these, which deck we were given, we have equal knowledge or kind of equal ignorance. We're going to assign a 50-50 probability for the prior probabilities for these 2 decks. There's 2 possibilities. We're given no information. We're just told someone picked one at random. Actually, it doesn't really matter how they picked them. From our point of view, we can't know. The other part, the first part, which is called the likelihood. So this part is called the likelihood, and unfortunately in English that has it's almost synonymous with probability, so it's a little it's kind of an annoying term in that way, but it's really the probability that we would see the data we have if we knew what the world was like. You know, if we knew that we had the low deck, what's the probability of seeing the data that we have? And then this is the prior probability. And what we are calculating eventually is this side, which is called the posterior probability, or the probability after we've seen the data. So the prior probability is the probabilities we have for our different states of the world before we see the data. All right, so earlier in the video we calculated out the 2 likelihoods for the probability of seeing a 7 and a 9. We got about 0.02. I'll say 0.021, say, and then we're multiplying by the prior, which is 0.5, and that's going to give us the about 0.01, and then the other probability is 0.0027. And we multiply that by 0.5, and we get times 0.5, 0.00135. Okay. Now this is what we're going to do to kind of change these probabilities to to actual probabilities, not proportional. We add these up to a number I call k, and so that gets me 0.01135. So that's what my k is, and then I go back and I redivide it. So what we have, I'm going to rewrite down here, given 7 and a 9 equals now the 0.01 divided by k. This is the low deck given the data we have, and this is the 0.00135 divided by k. All right, and in doing so, what we have then is just doing the calculation over 0.01135. I get about 0.12, and doing the other one, I get about 0.88. Okay, so these are the final probabilities of seeing the high deck and the low deck drawing a 7 and a 9. About 88% high deck, about 12% low deck. This follows our intuition that because the high deck has more high cards, drawing a 7 and a 9 is going to be more likely to be the high deck or the low deck. But it quantifies that intuition and tells you exactly how much more it's likely to be the high deck or the low deck given this particular data. There are two ways that one could calculate this. This is the first way where we kind of do all the data at the same time. I'm always going to calculate things in these two steps by essentially calculating out the top of Bayes' theorem first. That's this part here. That's the top. Adding up the results to get K, and then going back and dividing by K. And so we start there. We would then add them up. We get the K, and then we use the K over here. And what this does is it makes sure that all of the probabilities add up to 1. It just rescales it. You could do it all in one big line, but I don't find that to be particularly intuitive. So that's an application of Bayes' theorem. And if we had more data, if we drew more, we just simply follow the same procedure again and again.